And the next speaker is Alexandra Cyprianovic. I understand, Alexandra, that you pre-recorded your intervention. Is that right? I see you online.
I was planning to do this on Zoom and recording.
Okay, well, that's fine as well. Okay, so you can share the screen.
Let me see. Share. Okay, do you see the slides?
Yeah, perfect. So you're going to present Bridging the Gap Between Simulations and Survey Data, Domain Adaptation for Deep Learning in Astronomy. So please, you have 12 minutes, and the floor is yours.
Thank you so much. I'm very happy to be at this conference. I must admit it has been great so far. So thank you to all of you and to all of the speakers. So I'm Alexandra. I'm a postdoc currently at Fermilab in Chicago, the main building. Oh no, sorry. This always happens. 1 second. Okay, I'm back. So I'm going to tell you about some methods that we can use with our deep learning algorithms when we have the need to have a single model that works on multiple data sets at the same time. And in physics, that is very often the case. So I'm going to walk you through an astro example that I work on, but please feel free to extrapolate this to any kind of problem that you might have, because this is absolutely applicable to anything else that you might want to work on that includes multiple data sets. So the first thing that I want to talk about is what is domain discrepancy and what is the problem that we have. I will show you 2 domain adaptation methods and how to overcome these problems, and finally, hopefully, show you some results and convince you that this is useful. So first of all, in physics, and especially in astrophysics, when we want to use 2 different data sets, we often come to situation where we have small differences between them. So you might want to use 2 different telescopes, and of course you'll have different specs, and hence the images are going to look differently. But also, very often we want to first start from the simulated data. This is very useful because we know our simulations, we have labeled images, so this is a great starting point. And then you want to have your model work on the real data also, and especially if the data is new, is often going to be unlabeled. So the differences between simulated and real come from like 2 different reasons. One being that the simulations themselves, of course, will not mimic perfectly real physics and real observations. First, because we either don't know all of the physics, or we make approximations so that we can actually run the simulations and we have limited computing resources. And the second reason is that when you add observational effects to your simulated data, like observational noise or blurring by the point spread function of the telescope, even those things will not be perfectly mimicking all of the effects that you will have in real data. The thing that I'm going to talk about are merging galaxies. This is the thing that I really care about. And as you have heard in previous talks during this conference, studying galaxies and how they evolve is super important for understanding the evolution of the structures in the universe. And unfortunately, mergers are very long processes. And we need to leverage very large samples of merging galaxies if we want to understand this process very well. The problem with observations is that very often labeling large data sets is very much prone to errors and very slow, because you need scientists to go through like thousands of images and look at them. If you want to be very sure if something is a merger, you probably also need spectroscopic data. And all of these really lead to our necessity to be able to kind of combine simulated data where we know how the process evolves and real observations. So in this case, I will show you 2 different examples of different levels of difficulty. So in first example on the left, we want to have 2 data sets that will only slightly be different. So the source data set the one that we are going to pretend we know a lot about and we have labels for, is going to be distant merging galaxies from the Illustris simulation. So this is a really big simulation that evolves the matter in the universe from after the Big Bang to today. And I've extracted some distant merging galaxies, and I added the point spread function of the Hubble Space Telescope, so the PSF blurring. And this is the only thing that I added on these images. And then I'm going to pretend that I have real Hubble Space Telescope images, and I will add also the observational noise, and that will give me these bottom two images on the left. So I've made this example so that I have a very easy example where the two groups of images really differ only by the inclusion of noise and nothing else. The images themselves and the galaxies, they are the same. And I was able to make around 15,000 images by this process. So this is a super simple example. And then we want to see if the domain adaptation methods will work also on a real example, a more complex example. So in this case, we look at the right part of the screen, and we have merging galaxies again from Illustris. But because I really want to combine them with real data set, with observations, I will extract the final snapshot, so redshift 0 from Illustris. This means that I will have a smaller number of mergers to work with, which in itself is a little bit of a problem, but that's what we have to do. And then the target domain on the bottom is going to be real images from SDSS. And I'm using SDSS here because we have Galaxy Zoo labels so that we can test if this is working or not. Galaxy Zoo labels were created by human labelers. So this automatically means that only the easiest examples will have high confidence. And so if you look at the bottom row of images on the left where you have mergers, you see that most of them have bright two cores and obviously two galaxies near each other. So this automatically means that we have quite a large discrepancy between how the objects looks in the simulated and in the real data set. And also, again, in the simulated data, we don't have too many galaxies. Finally, I ended up by augmentations creating around 6,000 images to work with. So here in the second example, you have very small data sets and also very discrepant data sets. And we want to see in this super hard example if its domain adaptation will still make the neural network work in both domains. I want to apply this to a very simple neural network with just 3 convolutional layers and 3 dense layers so that we can see if this works, because this simple network does work very, very well on this data set if you just train and test it on the same data. So we know that this model works when you stay within one data set, but it does not work when you try to classify something from a different data set. So how do you do this in practice? You do this by adding something called a transfer loss on top of your regular classification loss. So this regular task loss, since this is a classification task, if we want to classify mergers versus non-mergers, in this case is just a regular cross-entropy loss that you see on the top. Now the main part is the transfer loss. This is the loss that adds domain adaptation part in the whole picture. So there are 2 different groups of methods when it comes to domain alignment and domain adaptation. One is on the left. So these methods include calculation of some kind of distance between 2 distributions and some kind of measure of how similar they are. And for this, we'll use maximum mean discrepancy, or MMD, which is a standard method used in statistics, where you use kernel methods to really calculate the similarity between 2 probability distributions. So there are many other methods. When it comes to MMD, for example, here on the left plot, you can see that if we want to, for example, see how similar are distributions of these blue and red dots, we can substitute them with kernels. In this case, these are Gaussian kernels in the simple example, sum them all up and calculate this witness function. So this witness function is this black curve. And it is a measure of how similar the blue and red curves are. So as the more similar they are, the smaller the black curve is going to be. So basically by minimizing, this witness function and adding witness function as a transfer loss, we are going to force the neural network to find features that are going to make the two distributions as similar as possible in the latent space and the way it represents the data set. So we're going to force it to find only domain invariant features and see the two data distributions as something that is similar so that we can overlap them and find common decision boundaries between classes. That's one side. And the other approach is adversarial methods. They have a completely different approach, but you will see that the result is the same, basically. So for that, we are going to use DANs, or Domain Adversarial Neural Networks. So on the plot on the right, when you have a regular neural network, you just have this green part, the convolutional layers that are extracting features, and the blue part that is doing the classification. But with DANS, you also add this pink branch that also has just dense layers, but very importantly, it has a gradient reversal layer before it starts, so that the loss in this branch is actually maximized. And this branch is trying to classify the domains. So basically, as the training progresses, the loss is getting larger and larger in this branch, and the neural network actually is becoming worse and worse at distinguishing between the domains. This means that the green part, the feature extractor, needs to find domain invariant features that are going to be useful for classification in the blue branch, but completely useless for classification of the domains in the pink branch. And in the end, by adversarially training these two branches, you end up again with domain invariant features. So basically, the important part why this is really good is that the training in both methods includes the labeled source domain, but also unlabeled target domain. And by training with the transfer loss, you find domain invariant features, and in the end, you can use your method on both domains. And you don't need labels. And this is super important even when the target domain is comprised of new observations. And you can see also, if we plot a t-SNE, so how the neural network sees these two distributions. You can see that before the training, the two distributions are completely separate, and they remain separate in the middle plot if you just train regularly. But if you use domain adaptation, you end up with a t-SNE on the right, where the two distributions overlap, so that you can find the common decision boundary and hope to find a model that works in both domains at the same time. So let's see some results. So first, in the example one, the simple one, you can see that without domain adaptation, the target domain is very bad. And also on the right, I'm showing you which regions of the image were the most important for classification into a merger class, something called a grad cam. And as you can see, the peripheries are the most important when there's no domain adaptation. That's because faint asymmetric features on the peripheries of the galaxies are super important. But the noise, unfortunately, dominates when you present it with the noisy target data set. And once you include either MMD or a DAN, you increase the accuracy by 20%. And actually, the neural network focuses on the centers, which are visible in both domains, and knows how to classify. And by the way, all of the results, you can find this in this paper that I'm quoting here on top. The same thing happens even in the hard example.
Sorry, less than 1 minute.
Yes, thank you. I'm almost done. So the same thing happens with the example 2, which is much harder. But as you can see in the table here, adding MMD doesn't really help by itself. And the reason for that is twofold. First, I'm reminding you, the data sets are super small and also very discrepant. So what we ended up doing is starting from the example 1 model and then fine-tuning the weights, so transfer learned features from the example 1 to example 2. And then we ended up with, again, a 20% increase in the target domain, which is at the same level as in the easy example. So even in this super hard example, domain adaptation seems very promising. And since I'm out of time, I will again leave you with these takeaways and thank all of my collaborators. And I hope that I convince you that domain adaptation is a promising tool that we should use for all of our cross-domain applications. But I want to, warn you that the easier the jump from one dataset to the other, the better the method will work. So when we're making our mock images from surveys, it's super important to try to make them as close as possible to the real dataset. Thank you so much.
Thank you very much, Alexandra. We have a few questions. We have time for 1 or 2 questions in the audience or Slack. Yeah, Michael.
Hi, this is Johannes Buchner. It's very cool work. I'm very impressed. I was wondering what your outlook is for inferring parameters. For example, the merger history or the mass ratio or things like that about the host galaxies, which you have accessible from the simulations?
That's actually a really cool question, and that's something that I'm thinking about and working on right now. I think this is going to definitely allow us to do that. I think it could be important to also include uncertainties, which I hopefully plan to do, so that we know how certain we are when we do something directly on one data set compared to when you try to merge 2 data sets, because I'm expecting that the uncertainties will become higher. But still, I absolutely believe that this will help us do that and to maybe start from the simulation and then allow us to do inference on different morphology parameters, shape parameters of galaxies or anything else that we care about on the real observations. I think this is possible, and I hope that, I'll hopefully soon show you that it is possible.
Yeah, we are slightly, so we can continue discussion over Slack. So I see that there are also, Alexandra, there is like one question over Slack, so I encourage you to check over there. So thank you very much. Another round.